Today we are going to look at a very important result in calculus, called the Squeeze Theorem, also known as the sandwich theorem. This theorem is especially useful when dealing with limits of functions that are difficult to evaluate directly. Theorem statement. Let I be an interval containing the point A. Let g, f, and h be functions defined on I, except possibly at a. Suppose that for every x not equal to a, we have g of x is less than or equal to f of x, and f of x is less than or equal to h of x. In other words, the function f is trapped or squeezed between g and h. Now, if both g and h approach the same limit L as x approaches a, then intuitively, f has no other choice but to go to the same limit. Formally, if the limit of g of x as x approaches a is L, and the limit of h of x as x approaches a is also L, then we conclude the limit of f of x as x approaches is equal to L. Proof using lim inf and lim sup. Let's first give a short proof using lim inf and lim sup. Since g of x is always less than or equal to f of x, and f of x is always less than or equal to h of x, we can compare their limits. So we take the limit inferior and limit superior of f. Then we get L equals the limit of g of x as x approaches a, which is less than or equal to the limit inferior of f of x as x approaches a, which is less than or equal to the limit superior of f of x as x approaches a, which is less than or equal to the limit of h of x as x approaches a, which is also L. So everything here is equal to L. Therefore, the limit of f of x as x approaches a must be L. This gives us the conclusion. Direct epsilon delta proof. Now let's look at a more formal proof, using the epsilon's delta definition of limit. Our goal is to prove that for every epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus it is less than delta, then the absolute value of f of x minus L is less than epsilon. To begin, we already know from the hypothesis that the limit of g of x as x approaches equals L. That means for every epsilon greater than 0, there exists delta 1 such that if the absolute value of x minus it is less than delta 1, then the absolute value of g of x minus L is less than epsilon. Similarly, because the limit of h of x as x approaches a also equals L, there exists another number delta 2 such that if the absolute value of x minus it is less than delta 2, then the absolute value of h of x minus L is less than epsilon. Next, we use the fact that g of x is less than or equal to f of x, and f of x is less than or equal to h of x. Subtracting L from all parts, we get g of x minus L is less than or equal to f of x minus L, and f of x minus L is less than or equal to h of x minus L. Now, to make both conditions hold at the same time, we choose delta to be the minimum of delta 1 and delta 2. Then, whenever the absolute value of x minus it is less than delta, we have negative epsilon is less than g of x minus L, which is less than or equal to f of x minus L, which is less than or equal to h of x minus L, which is less than epsilon. This shows that the absolute value of f of x minus L is less than epsilon. And that is exactly what we needed to prove. So by the epsilon's delta definition, the limit of f of x as x approaches a is L. This completes the proof. Remarks. Before we finish, let me highlight a few notes. First, the functions g and h act as lower and upper bounds for f. Second, the point A does not need to be inside the interval I. The theorem still works with one-sided limits. Finally, this theorem also applies when x goes to infinity. So it can be used in many different situations. So that is the Squeeze theorem, a simple but powerful tool in calculus.